right. I'll start off by saying behind me here on the wall, you'll see this week is a B day, and Mr. Brock will not be here. I won't be here on Friday, so I'm not holding any classes on Friday. And so why am I not going to be here? Because I'm going back to my high school. I'm going to Oklahoma on Thursday night. I'm going to be at homecoming pep assembly on Friday morning. I'm going to be in the homecoming parade. Going to go to the football game. It's my high school reunion. My high school reunion coming up this weekend. 40 years since I graduated high school. I'm kind of excited. And I knew we had like 200 in our class. I knew everybody. I was the student council president. I was in all of these clubs. I went K through 12 in the same school system. And so did a lot of my classmates. So we all knew each other. And in high school, Mr. Brock wore a mustache. I grew up when I was like 14. And so everyone would, so I don't think I can really grow one by Friday for the reunion. So they'll just, of course, I had a lot more hair than up here too, but I looked a lot like this in high school. So I said, I'm going to wear a mustache this week just to get in that old high school feeling there. But just something I'm playing around with. It was funny. I had it all through high school. I met my wife in high school. Of course, she wasn't my wife when I met her, but no, we started dating my senior year, her junior year. I actually proposed after we'd been dating for quite a while. I think it was 6 weeks. Yeah, it was 6 weeks. We started dating on March 5th, and I think I proposed April 20th. So it was very quick. But we were engaged 2 years before we got married, and she never saw me without the mustache. And so we got married, and we'd been married like a year or two. And I decided I'm going to shave off the mustache. I'm kind of tired of it. I've had it for several years now. So I shaved off the mustache, and my wife looked at me and she says, "You're growing that back now." Because when I shaved, I looked like I was 12. I had a baby face in my 20s. And she said, "It looks like I married a child from junior high. You're growing the mustache back." So I had to grow the mustache back when I shaved it off because my wife would not tolerate me looking like I was 12 years old after we were married. So I wore it several more years, and I don't know. Sometime in my 30s, I shaved it off, and now I play with it. Sometimes I have a beard or a mustache. Sometimes I don't. It's just but most of the time I don't. But this week I am just for the fun of it. So got to do something fun every once in a while. Just got to enjoy ourselves in life. All right, let's take a look at what we got. We got a couple of things going on in Algebra 3 this week. So I want to put this up on the screen, get us going. Let's look at our grade screen, and we see that we should have the first 2 lessons assignments done in Module 2. 2.1, 2.2 should be finished. We're ready for this week, 3 and 4. And we only have 1 lesson next week in the practice test. So this is a pretty short unit as well, especially when we take the lessons 2 at a time. But building functions from functions, and we're going to talk about inverse functions today. So we're going to go 2.03, 2.04. Some of you have, if you just turned in the test, I'm a little behind on some of the grading. Like if you're in my programming class, I'm working on that. If you got some of this, and some of these, I have to grade something. There's like an open response question as well. So I should have all the grading done by Thursday, but before I leave on Friday. But just know if there's a grade missing that you've turned in, it's because I haven't done my part yet to grade the open response questions. Okay, let's look at our scenic overlook for lesson 2.03. That's a little bigger on the screen. I like this. I must have done something better by the time I got to this lesson when I was copying all this. Combinations of functions. So 2 functions can be combined using addition, subtraction, multiplication, and division to form new functions. So we're going to look at some examples to see how new functions can be formed by combining operations. And in the quotient example, if we have f of x divided by g of x, why must we restrict g of x to where it cannot be 0, non-zero? And I'm sure you know that, and we'll talk about it as we get here. So let's look at it. We're going to define things. First, let f and g be 2 functions with overlapping domains. That's important. If they don't have overlapping domains, and one of them domain is only on the negatives and one's only on the positives, we won't be able to do some of these things. So we're talking about 2 functions that have overlapping domains. So then for all the x's that are common to both domains, so that's it. It has to be common domain areas. We can do the sum, the difference, the product, and the quotient defined as follows. So I'm actually going to write this down in our notes. I want to get some notes going here. So when we talk about, we got f of x and we have g of x as our two functions. So we can find f plus g of x. And we do that by taking f of x and adding it to g of x. We can find f minus g of x. And we'll do some example problems. So we're not just going to leave this hanging. Thank you, ma'am. Minus g of x. We can do fg of x by taking f of x and multiplying it by g of x. And we can do f divided by g of x by taking f of x and dividing it by g of x. So let me leave that up on the screen for just a moment there. F plus g of x, f minus g of x, f times g of x, f divided by g of x. All the usual stuff, add, subtract, multiply, divide, stuff we've been doing for years in our math classes since we were just wee little ones. All right, let's see what our lesson has to say about these things. This is also in our lesson, so if you haven't got this. Oh, yeah, we do have to add that. Oh, gosh, we were just talking about it. There's an extra caveat. And g of x, when you substitute x in, cannot equal 0. Can you imagine why? If we're dividing f of x by g of x, we cannot divide it if g of x equals 0, because we cannot divide by 0. That would create a problem. Big time warps, the universe explodes, all kinds of stuff like that when we're divided by 0. So we don't want to get into that mess. But yeah, f of x divided by g of x, but g of x cannot be 0. So, all right, composition of functions. We're also going to talk about this. Oh, yes. The composition of functions would be f of g of x. So let's talk about that. Composition would be, there's a way they write that. They do this. They do this f of g of x, and that's where we take f and substitute g of x into it. All right, f of g of x. We take g of x and we put it inside f of x. It may be written this way. This means the same thing as this. Take g of x and substitute it into f of x. But sometimes write f of g of x. And it could be g of f of x. It can go either way, right? It can go either way, but we have that there. So f of g of x equals f of g of x. So it says, oh, and that's the whole overview, but we're going to dig down into the lesson some now and look at some of their examples, because that's a nice little summary, but let's actually get to doing some of this. So there's that graph again that talks about the sum, difference, product, and quotient. But let's go down here and pull some examples from the lesson. Ah, perfect. So if we have f of x equals x squared, and g of x equals, oh, this is a good one, the square root of x plus 1. All right, and we want to find f plus g, f minus g, f times g, f divided by g, and g of g. Oh, gg. What, multiplying g times g? That's interesting. I guess we could do that. All right, so basically they want to go through all of these. But we could go through this as well, using this f of x and this g of x. So the first thing, I look at f plus g of x. So f plus g of x would equal, we just add them together. So x squared plus the square root of x plus 1. Simple as that. There's nothing to simplify. They don't have any common terms. It's just an x squared and then a square root of x plus 1. So since there's nothing to simplify, that's all f plus g requires. F minus g is almost the exact same thing. It's just that we're subtracting them instead of adding them. Hey, so far this is pretty easy stuff, right? F times g is x squared times the square root of x plus 1. We just put them together. There's not much to do with that. And let's see, the f divided by g of x equals x squared divided by x plus 1. And x cannot be, what would make this a 0? If x was negative 1, negative 1 plus 1 would be 0. So we have to limit the domain there because we cannot divide by 0. Now, g of x itself is kind of limited anyway to where x has to be a number that makes this positive. Because it's imaginary number if x plus 1 is a negative number. So it has to be, for this anyway, x has to be greater than negative 1. Now, for this equation by itself, x could be equal to negative 1. It's okay if this is a 0, but not when we divide it into f of x. By itself, x has to be greater than or equal to negative 1. For here, it can't be negative 1. And technically, that means it just has to be greater because we've already limited that. And then the other thing we can look at, they said g of g. So they went g of x, which we could do. And that one, you're multiplying the square root of x plus 1 times the square root of x plus 1. G of g times g, which means this is the square root of x plus 1 squared, right? Because it's multiplied times itself, which square root and square cancels that. So this just equals x plus 1. Kind of cancels itself out. And if we do, I want to do f of g. Let's do f of g of x. That would equal, we take x and we substitute g in for the x. So we take g of x. So we substitute the square root of x plus 1 for x. So that ends up the same as g of g. We got a square root. This just equals x plus 1. And if we go the other way around, g of f of x, we take g of x, the square root of x plus 1, but instead of x, we substitute in x squared plus 1. And that does not cancel out because this is not by itself. It's got a plus 1 in there. So that is where that ends up. But when we substitute g into f, we get x plus 1. When we substitute f into g, we get the square root of x squared plus 1. And this, there's no way that this can be a negative number, right? We don't have to limit any domain on this. Because if we're squaring x, if x is negative 10, it's going to be a positive number plus 1. If x is negative 1, it's going to be a positive 1 plus 1. It's always going to be a legal number. It's never going to be an imaginary number because we're squaring the x in that case. So that kind of cleans up the what's necessary to keep that a valid number by squaring it in there. So that's examples of how we use these functions and do these math things with the function on there. Just simply combine them. And then if there's simplifying to do, we'll do simplify. So let's see. Oh, and it lists the domain for each one. So F has the domain all real numbers, and G has the domain of -1 to infinity. Now, we talked about that up there. So since that is the domain -1 to infinity, you have to use where the domains overlap, right? Because the domain for this is all real numbers. The domain for this is x is greater than or equal to -1, so -1 to infinity. So when we combine these, we're limited to this domain. X is greater than or equal to -1. So we're limited to that all the way down, et cetera, et cetera, et cetera, because g of x does not exist beyond that. So we can't combine them except where they both exist at. And let's see, did they do? Oh, I was gonna say, what did they do with the one where we divided? See, they used a parentheses instead of a bracket. The bracket, when you write it in this fashion, the bracket says include this number. -1 is included. But when f divided by g, we use a parentheses, which say -1 is not included, but everything right up to it is. -0.99999 is included, but -1 is not. So you have to use the parentheses on that. And oh, they didn't simplify this. They said here we could express g times g of x as x plus 1, right? Because the square root of x plus 1 squared is simplified to x plus 1. But under the circumstances, x plus 1 would have the domain of all real numbers. But under these circumstances, it cannot, because it has two functions with a restricted domain. So we still have to remember this domain, even if we have that simplified. And then the composition of functions. Let's see. So they said if you have f of g, you got this g and this f, and you take it and put it in there, you're substituting. X must be in the domain of g, and g of x must be in the domain of f. So let's look at this here using these functions they have. So I'm going to write these down so I got these in our notes, and we can talk about them too. Let's see. So since they are using these two functions, e raised to the power of x, and e is a number, it's like 2.81, et cetera, et cetera, et cetera, and square root of x. If we take f of g of x, which means we take g of x and we substitute it in for x. So that makes this e raised to the power of the square root of x. Woo! That'd be an interesting graph, I would think. And this one, we take this and substitute it in for x there. So it'd be the square root of, instead of x, it's going to be e to the power of x. We just simply substitute it in, and there's no simplification to do with that. With the equations they're giving us, there's nothing that simplifies. See, verify numerically they're not the same. That's what they're talking about. F of g of x and g of f of x usually will give you two different equations, as it does in this case. These are not the same. F of g of x and g of f of x. There are circumstances where they can be the same equation, and we'll talk about those. Those are special circumstances. But I want to graph these to see how different they are, because I think those are some interesting looking equations. E raised the y equals e to the power of the square root of x. Okay, there is e raised to the power of square root of x, and it's kind of goes up into a parabola-looking shape. But it does something kind of weird right here at the bottom. It kind of is curving downward. But notice it does not go past 0, because we cannot take a square root of a negative number. So it does not exist over here where x is -1. We don't have a square root of -1. It stops right there at 0. And e to the power of 0 is 1 because anything to the power of 0 is 1. So that is the first equation. Let's look at the other one. When we do g of f of x, it is the square root of e raised to the power of x. So there you go. This is an asymptote. It gets closer and closer and closer to y equals 0, but it doesn't touch it. If we zoom in, zoom in a long ways, but we'll get there and see it. It is not touching the axis. Wow. We're down to 4 decimal points. It still says 0. Is it 0? Could it be 0? Hmm. We're way, we're way down deep in there. Oh, there it is. It's written in scientific notation. It's such a small number. That means that 1.85, you have to move the decimal over and put 23 zeros in front of it. So it's 0.0000000, 23 zeros, 185,349. Very, very small number. All right, let's back out of here so we can get out of there quicker. Okay, there we go. And then it shoots up to infinity. So those are two very different graphs for sure. But the composition of them would be limited to where they both exist, which is only, let's see, graphing them individually, e to the power of x is the green graph. It exists everywhere. And the square root of x exists only in the positives. That's the blue graph there. The blue graph is the square root of x. So they are not the same. They're different domains. F of g is only defined for x is greater than or equal to 0. Well, g of f is defined for all real numbers because when we look at the graph, it goes forever this way and it goes forever to the right. It just goes up really fast. So they are different, but they are very different. They are not the same. So let's see. One of the functions can be composed with the g functions to yield the basic f of g functions. So this is talking about graphing those. Finding the domain. We can graph them to find the domains easily, so you can see where it does and does not go. And they're showing it on a calculator. But when you graph these two equations, g of f and f of g, the graphs show that they have very different domains. So this has a domain of everything smaller than -1 and greater than 1, where this has everything greater than 0. So when you put f of g together and g of f together, it depends on how you put them. It could be very, very different. I like these kind of problems because we have some of these on the assignments. So we need to practice this because there's more than one answer. That's what I like to let you know is these problems have more than one correct answer. It makes it a little tough for me to grade because I got to check and see. It's like, okay, that's not the answer I had written down, but is it right? Yeah, let me show you what they're asking here. It says that h of x equals f of g of x. They've taken f and g and combined them. And they said, and this is what we get when we have h of x. It's x plus 1 squared minus 3x plus 1 plus 4. Now, this one, there's really one answer that everyone's going to see. It says find what was f of x and what is g of x. If we know that h of x is taking those two functions and putting g of x into f of x, it's f of g of x. Well, in this, we can look at that and say, okay, it must have been x plus 1 that was substituted in. So g of x must be x plus 1. So what if we take it back out? So this must have been x squared minus 3x plus 4. That one's not too bad. Okay, that must be what was substituted in because x plus 1 is squared, so it's x squared. So what if h of x was, let's see, what's their other example? The square root of x plus 3 plus 1. Okay. Oh, yeah, square root of x to the third plus 1. In that case, what is f of x and what is g of x? Not f of x twice. What is g of x? If h of x is this function, and it's those two combined, f of g of x, what was the original function? And you may have different answers on this. Some of you may say, well, f of x was x plus 1 as a square root, and this was x to the third. So they substituted x to the third in for x and got the square root of x to the third plus 1. Where somebody else may say, no, f of x was just the square root of x, and g of x was x to the third plus 1. So they substituted x plus the third plus 1 into for x and got the square root of x to the third plus 1. Those are both right. Those are both right. If they're just saying, here's h of x, what were they originally? It could have been this. It could have been this. Because either one of those, if you substitute this piece into here, you will get that. That's why I say sometimes there's more than one answer. So it's however you view it. And if you say either one of these, you'd get full credit because without defining what they were ahead of time, it could have been either one. I don't know if there's any other possible answers on that. You may come up with something that it could be, but for the most part, these are the two quick ones that just jump right out that it could have been this or it could have been this, either way to get that. So here's where they break the solutions down for these two problems. So here they said x squared minus 3x plus 4. That's what we wrote down and said it was x plus 1. So x plus 1 was substituted in. And then the other one, what did they say? Square root of x and x to the third plus 1. And then they give the other option. Could have been the square root of x plus 1 and it's x to the third. So, all right, I like that. Okay, it's just more examples of what we looked at with just tougher problems. And that's the end of that lesson. Let's look at the assignment that goes with this one before we go to the next one. So make sure we've covered everything they're asking. Here's f of x. Here's g of x. What's f plus g of x? Let's do an example on our own that's not in there, just in case. I don't know that they're going to give us a problem like this. If f of x equals 2x squared minus x, and g of x equals 3x minus 4, and we want f plus g of x, how do you think that's going to work? Well, we take f of x and we add to it 3x minus 4. Okay? But we need to simplify this. That's not our answer because we have like terms. Look, we've got a negative x and a plus 3x, positive 3x. So this would be 2x squared, negative x plus 3x plus 2x, and then we have a minus 4. So that would be the answer because we have an x in both of those, and when we add them together, we've got to account for that. If we're subtracting that, this can get a little tricky. This is where you really want to make sure and use parentheses sometimes. 2x squared minus x minus 3x minus 4. This is important to know when you're subtracting those. We're subtracting all of this, which means this simplifies to 2x squared minus x minus 3x plus 4. If we're subtracting a negative 4, this has got to be a plus. So that would be 2x squared. Negative x and negative 3x is negative 4x and a plus 4. So pay attention when you're subtracting. It's usually easier to put the second equation into parentheses so you remember I'm subtracting everything. Without that, we might just subtract the 3x and leave this as a negative if we don't put the parentheses. So make sure you don't make a careless mistake there of not subtracting every term. Subtract 3x, subtract negative 4. So, all right, let's go back and look at the assignment again. F plus G, F plus G, add those together. F times G. Okay, oh, let's do one kind of like that. F of x equals 3x squared. G of x equals 2x minus 1. And we want fg of x. We're multiplying those. We'll set it up. 3x squared times, and I recommend again the parentheses, because it's all of this function being multiplied by all of that function. Now, this function only has one term. It could have more than one term, but with parentheses, we have to distribute. So 3x squared times 2x is 6x to the third. And 3x squared times negative 1 is negative 3x squared. So that's what that would equal. Don't forget, you got to distribute. You got to multiply everything here times everything there. If this was 3x squared plus 1, we'd have to distribute two things because we'd put them both in parentheses. But don't get confused on that. And that's the kind of thing you have here. You got a 4x plus 6, and you got a 2x squared. And you're multiplying those two together. Multiply these together. 7x plus 7 and 6x squared. F divided by G. Divided by G. So you have to pay attention. Which one of these numbers can it not be? Because if you're dividing by G, G cannot be 0. You can't divide by 0. So figure out what number would not be allowed. And so which one of these would it be? F divided by G again. Different equations. F of G of X. Substitute G of X into there and simplify. And look, they pull a number out on this one. And here's another one, F of G. So there's 8 problems. So 2 F of G's, 2 divided by, looks like 2 multiply, 2 add. I don't see any subtracts. So, yes, I know I haven't done the assignment. Thank you. All right, let's look at our second lesson, inverse functions. So we've studied functions, but we learned that a function can be shown as a set of ordered pairs. So it says, for example, a function of x can be written as f of x equals 2x. So it's talking about, let's see, new sheet of paper. If we have f of x equals 2x, it says we could write it as a set of ordered pairs. Like when x equals 0, 2 times 0 is 0. When x equals 1, 2 times 1 is 2. When x is 2, 4. When x is 3, 6. Could write the function as a set of ordered pairs, right? And the domain is all of these numbers right here, domain. So we could select just the domain of 0 through 3 if we wanted to. We figured out the ordered pairs for this. Now this would be all real numbers, but we could decide to limit it, which would limit the range to be these numbers. So if our domain is 0, 1, 2, and 3, that our range would have to be limited as well to 0, 2, 4, and 6. So if we limit the domain, we've got to pay attention to how that limits the range. How that limits the range. And that's what they're talking about here. If the set of real numbers 1, 2, 3, 4 is the domain for the function, then the range would be 2, 4, 6, 8. And this is how they write that. F of x equals 2x. So they put the function first and then a colon and list the points. The points 1, 2, 2, 4, 3, 6, 4, 8. Now, if we take these points, which I did 0, 0, 2, 1, 2, 4, so mine's a little different than theirs. They went 1 to 4, I went 0 to 3. It doesn't matter. If we reverse them, which that one reverses and looks very similar, doesn't it? 2, 1, or 2, 6, 3, inverse. Oh, inverse. Oh, that's terrible. Oh, Mr. Brock, come on, man. Yep, it's got to get better. Brain's working faster than the hand. This is the inverse function of f of x. If we said these are the points from f of x, and we're using this domain, this is the inverse function. And we can call that f inverse of x in function notation. This would be f inverse of x. All right, I need to move that light to where it's a little better. F of x, f inverse of x. This would be the inverse of the original points, the inverse function. So, and we call that f of negative 1. Right, so finding the inverse, like the function is inverse, function undo each other. So let's set up and find what the inverse function is. So if the function is f of x equals 2x, first we change this to y equals, right? Step 1, change to y equals. Step 2, swap x and y. So this be x equals 2y. That's step 2. We've got to swap those, the x and the y. So the x becomes the y and the y becomes the x. Step 3, solve for y. So we do that by dividing by 2, and we get x divided by 2 equals y. So that. And then step 4, put it in function notation. I'll say put in function notation. So this will become f inverse of x equals x over 2. So we take the y back out, we put it in inverse notation. And so the inverse function is x over 2. Now, while we have the inverse, I want to look at something that we just looked at in the last lesson. If I have this equation, 2 of x, and I have g of x, that is x divided by 2. You recognize those two functions, right? And I said, I'm going to take f of g of x, which means I'm going to take 2 times x divided by 2. Well, 2 times x divided by 2 is just x. So that's what f of x equals. F of g of x equals x. How about g of f of x? We just looked at examples of the last lessons that these are not the same. In this case, x is going to be substituted for 2 of x. So 2x is substituted, f is substituting into the g, 2x is substituted. What's 2 times x divided by 2? This is x. In this case, f of g of x equals x and g of f of x equals x. That tells us these are inverses. And another secret I'll tell you, not only will they be the same, they will always just equal x. It's not that they'll both equal 3x or 3x minus 5. They'll both equal x. If it equals x, if both equals x, these are inverses. So that's how mathematically we can tell that it's an inverse. Mathematically. How else can we tell that it's an inverse? I'm going to look at this. I don't know if the lesson's going into this, but we're going to look at this. If we have y equals 2x, and we have y equals x divided by 2, so that's two of them, 2x and x divided by 2. Oh, I got to zoom way in. These are inverse functions. Oh, I'm zoomed too far in. Too far in. Okay, now why is that not working? Oh, because my scale is way off. Let's set them up both to be, how about 0 to 10? Or negative 5 to 10. Negative 5 to 10. And this will be negative 5 to 10. Got to have the scale the same. Negative 5 to 10 as well. Okay. There, now the graph looks right. They got the same scale. Inverses will reflect over the line y equals x. That's the blue line. So this function has the point 2.5, 5. This one will have the point 5, 2.5. Where's 5, 2.5? There it is, 5, 2.5. 2.5, 5, 5, 2.5. And it'll be the exact same distance from the blue line to the black line as is from the blue line to the red line, because they are inverses. They reflect over this line. See, the distance from there to there is the same as the distance from there to there. They have the opposite points all the way across there. Goes forever. So we can see graphically that they are inverses. So here's what they did f of g of x, where they took f of the inverse of x and it simplified to just be equal to x. And then they did it the other way and it simplified to be equal to x. So two functions are inverse functions if, for the functions f and g, f of g equals x for every value of x in the domain of g, and g of x equals x for every value of x in the domain of f. They will always equal x if they are inverses. So here's a test problem for us. Determine the inverse function of f of x equals 2x plus 2, and then prove it is by doing f of g and g of x. So if you have paper and pencil there, write this one down, f of x equals 2x plus 2. I'm going to write it down, and then I want you to start working through this. I'll work through it behind you, but here, I'll put those steps up again. Change to y equals, swap the x and the y, solve for y, and then put it back in function notation. I'll leave those steps up there for a moment. Let you get started, and then I'll catch up. So first we're finding the inverse. Over here, finding the inverse. So that first step we said was change it to y equals. All right, so hopefully you got that. What was the next step? Swapping. So next thing you want to do is swap. So this would be x equals 2y plus 2. That's all we do is just every x becomes a y, every y becomes an x. Step 3, solving for y. Hopefully you're ahead of me here. Solve for y, but you need it to be y equals again. That's what you're trying to do. Get it back to y equals. So the first thing you got to do, and you're Algebra 3, you know this one. You got to move the negative 2. X minus, this is Algebra 1 stuff here, just solving for y. Okay, so you got 2y on one side, you got x minus 2 on the other side. We're almost there. We don't have y equals yet. 2y divided by 2. And this cannot be simplified. Well, it can. You can rewrite it, but I'm gonna turn it around and put the y on the left. x minus 2 over 2. You can simplify it if you want to. It gets a little, you have to divide 2 by everything. This is really the same as y equals x divided by 2 minus 1. You can split the 2 under each one, but generally leaving it like this is fine. Right? Leave it like that. You don't have to do this. And the last step is to put it back in the function notation. X minus 2 over 2. So here. And it says, once you find the function, prove it's the function algebraically, which means take f and substitute the inverse function in. So take your 2x, instead of x, substitute. A lot of 2's in this problem. You're substituting the inverse function in for x. And then we're going to do it the other way. We're going to take f inverse and substitute f of x into it. So x minus 2 divided by 2. Well, instead of x, we're going to substitute 2x plus 2 minus 2 divided by 2. So there's the two problems you're solving. In the first problem, instead of x, you're putting this problem, x minus 2 divided by 2. In the second problem, instead of x, you're substituting 2x plus 2 in for the x. 2x plus 2 minus 2 divided by 2. I'll simplify those. There, I'm going to erase this just so I got some room there. So simplify this. This is divided by 2. This is multiplied by 2, which means those cancel each other out, right? So this equals x minus 2 plus 2. This equals x, because negative 2 plus 2. All right, how you doing? Are you done with this? Really don't need the parentheses because there's nothing to distribute. So we can just take out the parentheses, and it's 2x plus 2 minus 2 divided by 2. Well, plus 2 minus 2. So this is just 2x divided by 2, which is just x, because 2 divided by 2 is 1. So we verified, yes, we must have gotten the correct equation for the inverse, because when we checked it algebraically, it equaled x both times. So we did something right. It does equal x when we find the inverse. Okay, check your answer. Let's check our answer. So I'm going to click on that, open up this other window. Okay, it goes through these steps. F of x equals 2x plus 2 means that, oh, where'd it go? F, it keeps moving on me. There we go. F of x equals 2 plus 2 means that y equals 2x plus 2, because we change it from f of x to y equals. Then we simply switch the x's and y's, so now it's x equals 2y plus 2. Now resolve it for y, because it was y equals. Now we need to get back to y equals again. So you have to add, subtract 2. So it was 2y plus 2. Now it's x minus 2. And then divide by 2. And since this is a function, each x value produces only one y value, we can rewrite using inverse notation. F of negative 1 equals x minus 2 divided by 2. So then we have to prove this is, in fact, the inverse of our original function. So we take f of inverse x, we substitute that into our equation. So you get 2 times this plus 2. Well, 2 times x minus 2 divided by 2 is just x minus 2. X minus 2 plus 2 just equals x. And then substituting the other way, plus 2 minus 2 goes away, 2x divided by 2, it also just equals x. And that is exactly what we did on paper. So when we check our answers were correct. And the graph of an inverse function, I talked about that. It's over the line y equals x. Over the line y equals x. Let's graph these two new ones that we just calculated. I'll leave the y equals x line on there. So we had the first equation was f of x equals x, 2x plus 2, 2x plus 2. There's the first one. And the inverse function, I'll put it g of x on here just so Desmos is happy, is I got to use parentheses to put all of that in the numerator, x minus 2, and then it's divided by 2. And there it is, the reflection over the line y equals x. I think my scale is still just a little weird in here. Yeah, it's doing different numbers. So say -4 to 4. See if I can make that square look a little bit. Well, the screen is so wide. That's why the scale looks weird. I probably ought to do the x-axis from like -6 to 6 or something like that. That looks a little better. It would look a little distorted, but I have to do it wider than tall. So this looks the same distance because that should be exactly the same. The distance between those two. So if I get my scale right, but that is right. This goes through the point -1, 0, and this goes through 0, -1. Did that make sense? Because when we were talking about it on paper with the points, we said 0, 0, 1, 2, 2, 4, 3, 6, and the inverse, we reversed them. If we look at this, this is a y, and it becomes the x. This is a y, it becomes the x. This is a y, it becomes the x. Where on the other side, this is the x, it becomes the y. This is the x, it becomes the y. This is the x, it becomes the y. So it makes perfect sense that it would reflect over the line y equals x, because that's what's happened. The y become the x, and the x become the y. So it makes sense that when you graph it, this line would be perfectly in the middle of these two, y equals x, because the y does equal to x, and the x equals the y. They traded places. Here's another one for us to try. This one's a little trickier, so we should do this one as well on paper. F of x equals x to the third minus 3. And let's see, and then that's going to be the end of the overview, and it just gets into the more of the lesson. So let's see, f of x equals x to the third minus 3. So we want to find the inverse of this equation. That looks a little trickier. So the first thing we do is we make this y equals, then we trade places, x equals y to the third minus 3. Solve for y, add 3. So x plus 3 equals y to the third. Oh, y to the third. How do we get y? We take the third root. So y, I'm going to switch places, put the y over here and put that over there. Y equals the third root of x plus 3. And we can't simplify that anymore. X plus 3 is inside as the radicand, and we have the third root. So this is the inverse of the original equation. See, that's the equation, that's the inverse. Let's test to see if that really works. So let's substitute this back into there, right? So f of f inverse, let's see if we're right. X to the third, but not x to the third. We want the third root of x plus 3 to the third minus 3. Well, if we have the third root and we take it to the third power, those will cancel each other out. So this equals x plus 3 minus 3 equals x. Oh, that's a good sign. Now let's do it the other way. So the f inverse of f of x, the third root, instead of x, I'm going to substitute this in, x to the third minus 3 plus 3. X to the third minus 3 plus 3. There's nothing to distribute. That's just a 1 out there, so we don't need the parentheses. So you have minus 3 plus 3. So this equals the third root of x to the third, which is just x. X to the third and the third root cancel each other out. These are inverses. And let's graph those because that's going to be a little weird looking. Let's see, a little different for sure. So the first one is y equals x to the third minus 3. Oh yeah, look at that one. That's a little different. And the second one equals the third root. Oh, let me go down here and use our little extra functions in there because I'm not sure how to do third root. Let's see what options they have. Mm-hmm. Ah, here it is, the nth root. So we can put a 3 up there. And what was our equation? X plus 3 underneath. And there it is. Look at there. It does reflect over the blue line. Kind of weird looking, but it is a perfect reflection. The same distance both directions. This crosses the axis at -3, 0, which means this should be at 0, -3. Pretty cool. All right, check our answer. Let's pull this up and see. It should be right because we verified graphing it and by finding both of them equals x when we substitute them into each other. They show the graph as a way to solve that. There you go. So there it is, reflecting over it perfectly. Very nice. And they graphed it as x plus 3 to the 1/3 power because that's the same. That's the same as the third root of raising something to the 1/3 power. That's what Algebra 2 studied today, coincidentally. But they are symmetric around y equals x. Marvelous. Now here's a key thing though. Not all functions have an inverse function. Not all functions have an inverse function. Let's look at one of those. Y equals x squared. Y equals x squared. Does that have an inverse function? Y equals x squared. If we'll reverse that, x equals y squared. So y equals the square root of x. And when you take the square root, it's really plus or minus, right? But plus or minus the square root of x. So if we do y equals the square root of x and also the negative version of that, negative square root of x, there's plus or minus the square root of x. And I can change that to be green as well. Oop, that's not what I wanted. Green. Okay. Yes, we calculated an inverse. There's the inverse of the original. Well, let's make the original one red since we have a blue line as our reflection line. But here's the thing, it's not a function. It fails the vertical line test. There's 2 y's for the x's. So that's why it says not all functions have an inverse function. Because the inverse of y equals x squared is the plus or minus the square root of x, which is not a function. And then they give that same example. An example of a function without an inverse would be f of x equals x squared. because the 2 and the negative 2 in the domain point to the element 4. So when you reverse those, 4 has 2 and negative 2. So it has an inverse, but the inverse is not in function, so it doesn't have an inverse function. For most functions, we must follow our process to determine the inverse function. Just replace the f of x with y, replace every x with y and y with x, and solve for y. And then check for the validity of the inverse function by proving the identity function. So, all right, and then it gets into more details, more examples of the exact same thing we just talked about. Let's look at the assignment that goes with this. Find the inverse of this function. Okay, so they give you an equation and you find the inverse. Unless it's not a one-to-one function. Maybe when you find the inverse, it's not a function because it doesn't pass the test. It has more than one y for an x. Find the inverse of this function, x to the third minus 8. Find the inverse on that is different there. This is the third root of x plus 8. The plus 8 is not in the square root or third root symbol, so that's different than this one. Find the inverse of this function. Determine, is this function one-to-one? We may go back and look and see what they define one-to-one just to make sure, but it should be 1y for every x, right? That means each and every one-to-one should be each and every y has one x, each and every x has one y. It works both ways. One-to-one means only one x to one y and only one y to one x. It works both ways. So you have to look at that and say, is this a one-to-one function? Oh, and here's one that you do algebraically. Fill in the blank. Confirm that these are inverses. And look, it's the same equation. 2 over x and 2 over x. Are those inverses of each other? Could they be inverses of each other? It says prove that they are by doing this substitution. Substitute g of x and f of x. Substitute f of x and g of x and simplify and see, do they just equal x? If they just equal x, they're actually an inverse of themselves. 2 over x and 2 over x are inverses of itself if you can prove that they equal x when you substitute. Interesting. So let me give you a tip on that one, because that one gets a little confusing, because you're like, wait a minute, 2 of x over 2 of x. All right, third sheet of paper. If you have 2 over x and you substitute 2 over x, so you end up with 2 over x, right? If this equation, and we say the inverse equation, if they're both 2 over x, when you substitute this one into the x, you got 2 over x. What do you do with that? You got a fraction with a fraction on the bottom. Well, the way you get rid of a fraction on the bottom is you multiply the top and bottom by the inverse. So let's say, I'm just going to make up one here. If I have 5 over, and I'm just going to make up different numbers, 3 over 4. Like, wait a minute, I got a fraction, and I got a fraction on the bottom. If I multiply by 4 over 3, top and bottom, right? So I'm multiplying by 4/3 over 4/3, which means I'm just multiplying by 1, right? Because 4/3 divided by 4/3 is 1. What happens is, multiplying this is 20 15. Oh, no, thirds. No, yeah, 20 thirds, because 5 is the same thing as 5 over 1. So this is 20 thirds on top. On bottom, what do I get? 12 over 12, which means this is just 1. So 20 thirds over 1 is just 20 thirds, because anything over 1 is just whatever it is. So look, I got rid of the fraction on the bottom by multiplying by its reciprocal. You just reverse this. So this I'd multiply by x over 2 and go from there. Multiply. So I'm just multiplying by 1. I just write 1 like this in a real way, a weird way. And you can simplify it that way. So there's a little hint on how to do that last problem, because it's like, okay, that looks weird. 2 over x and 2 over x. But the problem says confirm their inverses, which kind of implies that they are inverses and you're just confirming it. So interesting. Interesting. Okay. Any questions over that? This lesson's not too bad. Things we can do with functions, add them together, subtract them, multiply them, and putting one inside the other. That's the one that's kind of interesting. Take f of g of x, take g of x and put it inside f of x, substitute for x, see what you get. And that led right into the inverses, because we've got to know how to do that to determine is something an inverse. We just substitute it into the other equation both ways. And if it equals x, it is in inverses. So, all right. Well, we finished about 20 minutes early, which means you got 20 minutes if you want to get these week's assignments done before advisory. You got 30 minutes before advisory because you got that little break in between this class and advisory. So I'll give you the rest of the time for yourself then. You can use the rest of the period to work on the assignments or whatever you need to do. And I'm here if you got questions, but otherwise, have a great week. We will have class Thursday. I won't have class Friday.